Okay, it's great to have so many people joining us for today's SMRI Algebra and Geometry online seminar. We're very happy to have Lauren Williams from Harvard University speaking today about the totally asymmetric simple exclusion process on a ring, Schubert polynomials, and evil avoiding permutations. So Lauren, please take it away.
So thank you so much. It's great to be here. I'm going to be speaking about joint work with Donghyun Kim, who's also at this meeting, and he'll be applying for postdocs in the fall. The work I'm speaking about is based on this archive preprint, whose number I put on this first slide. So I want to start by giving an outline of my talk. I'm going to first explain what is the exclusion process on a ring. I have a little schematic in the upper right corner, which I'll explain in more detail. Then I want to talk about the stationary distribution of this model. This is a discrete time Markov chain. It has a nice stationary distribution. And the stationary distribution is connected to Schubert polynomials. And then I want to explain some results, including a conjecture called the monomial factor conjecture, and some results to do with a class of permutations that we call evil avoiding permutations. Okay, so let me first just give a little bit of background on the exclusion process. This is an old model introduced by biologists around 1968, and it was introduced independently by mathematician Spitzer in 1970. Now, in this model, we have particles hopping on a one-dimensional lattice. So the lattice could be something like this or like this. At most, one particle is in every site, and the particles could have different weights which affect their hopping rates. And I'm indicating their weights by the numbers inside these circles. The lattice, there's many choices for the lattice. It could be a line with open boundaries, or it could be a ring. Today, I'll primarily be talking about a ring. And the model was introduced by biologists as a model for translation in protein synthesis, and has also been cited as a model for traffic flow. And the ASEP has been extensively studied. There's more than 1,000 papers on the archive, and this is a very incomplete list of names of people who have worked on the model. So now let me define the version of the ASEP we're interested in. So this is going to be the inhomogeneous TASEP on a ring. So what we're going to do is fix a lattice of n sites on a ring, and it's going to be filled with particles of weights 1, 2, up through n. I could allow particles to have repeated weights, but to make most transparent the connections to Schubert polynomials, I'm just going to stick with the situation where the particles have weights precisely 1 through n. So now this is I'll define it as a discrete time Markov chain. There are n factorial states, which I identify with the permutations on n letters, and I will identify them with permutations by choosing some fixed but arbitrary place to cut open my circle. So I'm cutting open the circle, and then I identify the state with a permutation in the symmetric group on n letters. And in this example here, I would identify my state with the permutation 1, 4, 6, 2, 7, 8, 3, 5. So I'm just reading clockwise. And now I need to define the transitions in the Markov chain, which are as follows. So if I is less than j, then the probability of transitioning from a state which has particle of weight I next to particle of weight j to the same state obtained by swapping j and I will be xi minus yj. And if I is greater than j, then the probability of going between these two states is 0. So we call this totally asymmetric because we're only allowing hopping in one direction, namely when the smaller particle is counterclockwise of the larger particle. And then they swap places. Yeah, if there's any questions about the definition, feel free to interrupt or put it in the chat.
And x1 up to xn and y1 up to yn are just indeterminants.
Yes, yes, yes. Xi and yj are indeterminants, yes, which will subsequently be related to variables of Schubert polynomials. Okay, so now a natural question is, what are the steady state probabilities? In other words, when time goes to infinity, what is the probability distribution that we will see? So let me first make some notation. So for a state, which is a permutation, I'll let psi sub w be the unnormalized steady state probability of being in state W. So now what do I mean by unnormalized? Well, if we compute this probability distribution, then all of my steady state probabilities will be rational expressions in the xi's and yj's with a polynomial numerator, polynomial denominator. But what we want to do is put everything over a common denominator, and then we clear the denominator. And what's left is what I'm calling unnormalized steady state probability. Okay, now let me first make a small observation, which is that there is, of course, a circular symmetry in the model. And what that implies is a corresponding identity on these steady state probabilities, which I'll just write out as with an example. The steady state probability of being in state 3, 1, 2, 4, this is in the case n is 4, is the same as the steady state probability of being in state 1, 2, 4, 3, is the same as the probability of being in state 2, 4, 3, 1, is the same as the probability of being in state 4, 3, 1, 2. So we can restrict our attention to states or permutations where the first letter is 1. Okay, so now let me just show what some of these unnormalized steady state probabilities look like. So this is the case. N is 4, and of course there are 4 factorial different states, but by the circular symmetry, I can just write down the steady state probabilities for the states identified with permutations starting with 1. And these are the probabilities, the unnormalized probabilities that you get. Oh, sorry, and I should say, for simplicity in some of the examples, I'm showing the probabilities where I've set y sub I equal to 0 for all I. So what we have in this little example is that in these cases, psi sub w is a monomial times a product of Schubert polynomials. And my notation here is that this math frac S sub w is the Schubert polynomial associated to permutation w. So I will define Schubert polynomial concretely in a little while. But let me first just take a step back and just say, okay, what are some main questions we can ask here? So so a first main question from combinatorial point of view is to find a combinatorial formula for the steady state probabilities. And a second question is to figure out those monomial factors on the previous slide and the relationship of these steady state probabilities to Schubert polynomials. Okay, and to sort of broaden the picture a little bit more, I actually want to point out that there are several versions of the exclusion process on a ring, which have very interesting and somewhat parallel properties. So, so I've made this little chart here, and at the left is the model that I would refer to perhaps as the usual multi-species ASEP. And this model is simpler in a way in that hopping rates are either 1 or t. So I'm allowing, so when particles hop, when the smaller particle is counterclockwise of the larger one, these two particles are allowed to exchange places at rate 1. But if the larger particle is counterclockwise of the smaller, then they're allowed to switch places at rate t. So this model is a little bit more general than what we talked about previously in that particles can hop in both directions. But on the other hand, it's simpler in that our hopping rates are either 1 or t, and not these more complicated rates with the xi and yj. And in this usual multi-species ASEP, essentially everything is known. So there's a formula for the steady state, for all steady state probabilities in terms of some objects called multi-line queues. I'm not really going to go into the definition, but I've drawn an example of a multi-line queue, and formulas were given here by James Martin, and then a slightly different but very similar formula was proved in a different way in our joint work with Sylvie Cortiel and Olia Mandelstam. Okay, so that's the setting. That's for the setting of the usual multi-species ASEP. And now if we go
Laura,
to the...
I have a question.
Uh-huh.
Should I think of the labels of the particles as weights associated to them? Or what is the significance of...
Oh, yes, absolutely. Yes. Think of the labels on the particles as weights.
And so could you also have models where two particles have the same weight?
Yes, yeah. Absolutely. So we could allow particles to have the same weight. And in fact, the results I'm going to put on this slide hold in that more general model. But I introduced the inhomogeneous TASEP on my previous slide, where particles all have distinct weights, only because it'll make the connection to Schubert polynomials more transparent later. Yeah. Yeah, so anyway, so in particular, formulas here are for the model where you allow particles of repeated weights. Okay, and now if we go to the situation of the inhomogeneous TASEP, then in the case when y sub I is 0, there are formulas for the probabilities. Also, in terms of multi-line Qs, although with a very different weighting scheme. And this formula had been conjectured by Iyer and Linnison and was proved by Arita and Malik. But there's no formula actually in the general case where the y sub i's are non-zero. Interestingly, it's a lot harder when you allow the y's to be general. Okay, so this is, so basically in these two versions of the ASEP on a ring, there are combinatorial formulas for steady state probabilities in terms of multi-line Qs, although not in complete generality in the case of the inhomogeneous TASEP. Now, interestingly, the usual multi-species ASEP has a connection to Macdonald polynomials. Macdonald polynomials are a QT generalization of Schur polynomials. And just to say a little bit about what this connection is, if one looks at the partition function for the ASEP, and maybe I'll just take a moment to say what is the partition function. If you compute all your steady state probabilities for the multi-species ASEP, and you put them all over a common denominator, that common denominator is the partition function. And it turns out that the partition function equals the Macdonald polynomial p sub lambda of x1 through xn qt when you've specialized almost everything to 1, xi equal to 1 and q equal to 1. So you only have the t parameter remaining, and where lambda is obtained by sorting the particle weights, so the weights of the particles that you see on the ring, in weakly decreasing order. And this was shown by Cantini, De Geer, and Wheeler. And then more generally, each steady state probability is a specialization, the same specialization of what's called a permuted basement Macdonald polynomial. Permuted basement Macdonald polynomials are a generalization of non-symmetric Macdonald polynomials. And then we showed this paper with Quartil and Mandelstam. And I'll just mention that one sort of very nice application of this connection between ASEP and Macdonald polynomials and the fact that there's this combinatorics of multi-line Qs describing steady state probabilities of the ASEP is that we found that we could use multi-line Qs to give formulas for, so new formulas for both Macdonald and permuted Macdonald polynomials. Okay, so that is the situation for the usual multi-species ASEP. Now, on the other hand, if we go to the inhomogeneous TASEP, this model is connected to double Schubert polynomials. And anyway, I find this sort of very fascinating because Macdonald polynomials and Schubert polynomials both generalize Schur polynomials, but in very different ways. So anyway, so to say something about this connection to the Schubert polynomials, in 2012, we wrote a 4-page paper describing some conjectures connecting this model to Schubert polynomials. That was this 4-page paper with Lamb, where we basically wrote some conjectures and had no proofs. And then in 2016, Cantini showed that n of the n factorial states have probability psi sub w, which is proportional to a product of double Schubert polynomials. And then in this 2021 paper with Donghyun Kim, we showed the same sort of statement as above, but for approximately 2 plus root 2 to the n minus 1 over 2 out of n factorial states. And we believe that these are the only states where the steady state probability is proportional to a product of Schubert polynomials. So conjecturally, all other psi sub w can be written as non-trivial sums of Schubert polynomials. Okay, so these are the 2 versions of ASEP on a ring and the connections to Macdonald and Schubert polynomials. Okay, now I've said Schubert polynomial a bunch of times, I should probably define it.
Sorry, Lauren, before you do that, can I just ask you, is there any hope of a common generalization of these 2 sides?
So there is a hope, and that would be very cool. Although when one looks at steady state probabilities, if you take, say, the inhomogeneous TASEP and start letting particles hop in the other direction, the number of terms in the steady state probabilities on the partition function sort of blows up in a very ugly way. So, well, I think the answer is, well, okay, actually, okay, maybe I guess I don't want to sort of make a claim, but just to say that the combinatorics on either side starts to get rather ugly when you try to generalize the model, moving it more towards the other. Yeah.
Can I ask another question? When you say non-trivial sum of polynomials, do you expect the coefficients to be 1?
Oh, that's a good question. I don't know. I'll show the example for n equals 5 in a little while, and they do look to be 1, but I'm not sure I would want to make a claim about that. Okay, so now let me just review the definition of Schubert polynomials for those of you who know already, or give the definition for people who haven't seen it. So I have to define what's called a divided difference operator, which is an operator on polynomials in n variables. So if p is my polynomial, then del IP is equal to what I get when I take my polynomial p, subtract off the same polynomial after having swapped xi and xi plus 1, And then this difference is divisible by xi minus xi plus 1, so we divide by it. Okay, and the result is called del IP of, well, okay. So this is the effect of the divided difference operator. And now if SI1 through SIM is a reduced expression for some permutation W, then this sequence of divided difference operators depends only on W and not on the reduced expression. So we can denote that operator by del W. Okay, and now Schubert and double Schubert polynomials will be defined inductively. So X is the set of variables x1 through xn, and Y is going to be my set of variables y1 through yn. And delta of x comma y is going to be this product of linear factors. And now to each permutation W, we associate the double Schubert polynomial, which is obtained as follows. We start with this delta of x comma y, and then we act on it by the divided difference operator associated to the permutation W inverse W naught, where W naught is the longest permutation. In this expression, the divided difference operator acts only on the x variables. And if all the y's are 0, then we get back what's known as the usual Schubert polynomials. Right, so ordinary Schubert polynomials are a specialization of the doubles. And if W in Sn is a Grassmannian permutation, meaning it has a unique descent, then this Schubert polynomial is a Schur polynomial. And in particular, both Macdonald polynomials and Schubert polynomials generalize Schur polynomials. There's a nice geometric significance, which is that Schubert polynomials represent the cohomology classes of Schubert varieties in the complete flag variety. There's also a geometric interpretation for double Schubert polynomials. And there's been a lot of work finding combinatorial formulas for Schubert polynomials, including Billy Jokish-Stanley, Fomin Kirillov, Konert, and others. Okay, so now let me show the next table of steady state probabilities. So this is the inhomogeneous TASEP when n is equal to 5. And let me just explain my notation here. So if I write something like x to the 5 to 0, that stands for x1 to the 5, x2 squared, and x3 to the 0. And I'll just point out here that most of our unnormalized steady state probabilities psi sub w have the form monomial times product of Schuberts. There's a few exceptions. There's this one here. We have a non-trivial sum of Schuberts. This one here is a sum of 6 Schubert polynomials. This one here is a sum of 2. This one here is a sum of 2. But apart from that, they all look like monomial times product of Schuberts. And another thing I'll point out is that if you look at the monomial factors that appear here, they are all distinct. So let me actually talk about those monomials now. So this conjecture comes from our 2012 paper. So let's let W be a permutation where when I write it in list notation, the letters are W1 through Wn. And let's let R be the position where I plus 1 occurs, and S be the position where I occurs. And I will let alpha I of W be the number of integers greater than I plus 1 when I scan the letters of my permutation starting at I plus 1, wrapping around if necessary, but ending at I. Okay, so if my permutation is 1, 4, 2, 3, 5, then what you could imagine doing is putting 1, 4, 2, 3, 5 on a circle, and if I is equal to, let's say 2, then what I'm doing here is I'm going to start at I plus 1, which is 3, and I'm going to scan the numbers as I go, as I wrapping around, if need be. Whoops. Okay, start at I plus 1, look at all the letters in order, stop when you get to I, and count how many numbers are bigger than I plus 1. And so here I've seen 2. So that's alpha sub I of W. Okay, so now I can write down the first result. So we consider the inhomogeneous TASEP on the ring, and this is where y sub I is 0 for all I. So now for W, a state, let's let eta of W be the largest monomial factor that can be factored out of psi sub W. Then the statement is a precise formula for eta of W. It's the product as I goes from 1 to n minus 2 of xi to the alpha I of W plus alpha sub I plus 1 of W plus alpha n minus 2 of W. So just to sort of unpack what this numerator is doing, if we think about alpha n minus 2 of W, we're going to be starting at the letter n minus 1 in the permutation, and we're going to read letters in order until we get to n minus 2, and we'll count the numbers that are bigger. That's this part. And then since we have an alpha sub n minus 1 of W, we're going to continue from n minus 2 and scan the letters until we get to n minus 3, count how many numbers are bigger than n minus 2, and we'll keep going until we get down to I. Okay, so this is the precise formula for the monomial factor. And then the other part of the statement is that if two states, W and W prime in Sn, have the same monomial factor, then W and W prime are the same up to cyclically shifting. They're cyclically equivalent. Just meaning that, I think I had an example at the beginning saying that, psi sub 1, 4, 2, 3 is the same as psi sub 4, 2, 3, 1, and so on. So that's what I mean by cyclically equivalent. Okay, so let me do a tiny example. Let's stick with that example. W is 1, 4, 2, 3, 5. So we can put our numbers on the circle as I did before. And then alpha 1, so to compute alpha 1, I'm going to start at 2, and wrap around until I get to 1 and count how many numbers are bigger. So I saw 2 bigger numbers, 3 and 5. And then to compute alpha 2, I'm going to start at 3, wrap around until I hit 2, count how many numbers I see that are bigger. And there are 2. And finally, to compute alpha 3, I will start at 4, wrap around until I get to 3, count how many numbers are bigger, and that's 0. And so by the formula, eta of W should be x1 to the alpha 1 plus alpha 2 plus alpha 3, x2 to the alpha 2 plus alpha 3, x3 to the alpha 3, and this will be x1 to the 4, x2 squared. Okay, so this was the example where W is 14235, and I got this monomial. And now let me go back to my example. That was 14235, and we see the monomial x to the 420. Okay, so that's an example of this monomial factor conjecture theorem. Okay.
Lauren, there's been a discussion in the chat about the issue of whether an expression in terms of as a sum of products of Schubert polynomials would be unique.
Oh, if I factor out this monomial factor, then Schubert polynomials form a basis for the polynomial ring. So that sum, so the remaining sum will be unique.
Schubert polynomials form a basis, but here you're talking about sums of products of Schubert polynomials.
Oh, sorry. The statement. So I'm writing my polynomials as monomial times sum of Schuberts.
Sure, but some of the examples lower down in this table have products of Schuberts.
Oh, yes. So so basically I will shortly give an example. Right. So sure. So I could certainly take a product like this and express it as a sum of Schuberts. That's absolutely true. So what we were doing when we first looked at this data was noticing that many states looked like monomials times products of Schuberts. And so what we first tried to do is factor out the largest monomial. Then we try to see, is the resulting quantity a product of Schubert polynomials? If so, write it as a product of Schubert polynomials. Otherwise, write it as a sum of Schuberts. Yeah, hopefully that was clear. That was a good question.
Thanks.
Okay, so so now I want to talk about these products of Schubert polynomials that we see. And in order to do that, I need to mention something called pattern avoidance. So we say that a permutation, W, equal to W1 through Wn, avoids the pattern 2, 4, 1, 3 if there are not 4 positions, I less than j less than k less than L, such that Wi, Wj, Wk, Wl are in the relative order 2, 4, 1, 3, meaning that this is the smallest, then this one, then this one, and then this one. So as an example, if W is the permutation 3, 4, 6, 1, 2, 5, and if I look at the letters 3, 6, 1, 5, then they have the relative order 2, 4, 1, 3, So we say it contains the pattern 2413. On the other hand, W prime, the permutation 1, 2, 6, 4, 3, 5, has no 4 positions which have the relative order 2, 4, 1, 3. So we say that it avoids the pattern 2, 4, 1, 3. Okay, and now we will say that the permutation W is evil, avoiding, if it avoids the patterns 2, 4, 1, 3. And I'm going to identify these numbers with the letters E, V, I, L, evil, and also the patterns coming from the following anagrams of evil. So we have the word vile, and if I make the same identification between the letters VILE and the numbers 2, 4, 1, 3, then this gives the pattern 4, 1, 3, 2, and also veil and leave. And these give the patterns 4, 2, 1, 3, and 3, 2, 1, 4. Okay, leave is a little bit of a stretch. It's a Scandinavian name, but that was the best that we could do. Anyway,
how do you actually search for words with a
yeah, you
given
can
collection of anagrams?
You can find anagrams online, at least for short words, for short lengths. Yeah. Yeah. Anyway, this was the best we could find. And it's, yeah, I don't know of any other way that I could possibly remember like these 4 random sequences, these 4 random permutations. Okay, so
in particular, this collection of permutations is not closed under taking inverses.
Correct. Yes. Yes. Okay, so then I can state a theorem, and I'm going to first state it in a slightly vague form. Let's let W be an evil avoiding permutation. And since we're thinking about the TASEP, which has this circular symmetry, we can assume that W1 is 1. Then the unnormalized probability psi sub W is proportional to a product of K double Schubert polynomials, where K is the number of descents of W inverse. And if anyone doesn't remember the definition of descent, a descent of a permutation V is a position I such that Vi is bigger than V sub I plus 1. Okay, so yeah, so basically in this situation, our probability psi sub W can be written as the monomial factor, the one I showed before, times the product of K double Schubert polynomials. And I'll make that more precise momentarily. But first, let's just go back to this data again. So let's recall that evil is 2413, vile is 4132, veil is 4213, and leave is 3214. And if we now go to the 4 states where the probability was written as this non-trivial sum of Schubert polynomials, well, this first permutation, if you ignore the 1, it contains the pattern 2, 4, 1, 3. This one contains the pattern 3, 2, 1, 4. This contains the pattern 4, 1, 3, 2. This contains the pattern 4, 2, 1, 3. So these are exactly our four bad anagrams. And also remember, there was this statement that the number of Schubert polynomials that appear is the number of descents of W inverse. If we look, say, at this permutation here, its inverse has 3 descents, and the probability here is written as a product of 3 Schubert polynomials. Okay, so I'll just say a little bit about these evil avoiding permutations. So let's let E of n be the number of evil avoiding permutations in Sn. Then E of n is, there's a simple expression for E of n. And this sequence of numbers appears in the Sloan Online Encyclopedia as sequence A006012. So evil avoiding permutations themselves, I have not seen occur anywhere in the literature, but their number does appear. And so we can see from Sloan, E of n also counts various other classes of permutations, including what are called rectangular permutations on 1 through n, which are those avoiding 2, 4, 1, 3, 2, 4, 3, 1, 4, 2, 1, 3, and 4, 2, 3, 1. And let me just write down this again. So somehow the number of permutations, so we do not have a bijective proof, but apparently the number of permutations avoiding these 4 patterns is equal to the number of permutations avoiding these 4 patterns. Seems to be not obvious. And there's some other interpretations in Sloan as well, but we don't have any bijections between our interpretation and any of the others.
Sorry, can I ask another question? In your theorem, you were only considering permutations which start with W1 equals 1. So
yes.
The evil avoiding condition only applied in that representative of the cyclic equivalence class.
Yes.
So the count you just told us was for all the evil avoiding permutations in Sn?
Oh, yes, but that'll just result in a shift between Sn and Sn minus 1 or something. Since if I...
Oh, yeah, okay. Oh, yeah, okay. Sorry. Yeah.
Okay, so now let me just make the theorem I mentioned earlier a little bit more precise. So I want to explain what are the k Schubert polynomials that will occur in this product. So let's let W be in Sn be evil avoiding with k, such that its inverse has k descents. Then there are partitions lambda 1 through lambda k. And if we use those partitions to define another vector mu, like this, then psi sub w is equal to x to the mu times the product of, so now I'm going to write so each of the Schubert polynomials that occur is actually a flagged Schur polynomial. And let me just explain my notation. This is a flagged Schur polynomial. If you're familiar with the combinatorial definition of Schur polynomials in terms of, where you write down a generating function for semi-standard tableau, flagged Schur polynomials can be defined the same way, where we fix the shape, but we just put a bound on entries in each row. So with entries in row J bounded above by n minus lambda J I. And to construct these partitions, we let C be the lemma code of W inverse, and then we let A0 be 0 and A1 through AK be the descent positions of C1 through Cn, and then what's lambda I? It's just equal to this vector n minus AI to the AI minus something to do with the lemma code. Okay, so anyway, this is just to say that there's a easy, concrete way to write down these partitions and then these Schubert polynomials. And the way that I'm stating this theorem here, it's in the setting where y sub i's are equal to 0, but essentially the same construction gives the double Schubert polynomials as well. Okay, so so this is a little table now restricted to the evil avoiding permutations, and these are the tuples of partitions associated to the states, and then these are the associated unnormalized steady state probabilities. Okay, so let's see. I guess I want to wrap up here, so I'll just make a few comments about the proof of this theorem. So the first thing one might try to do is prove the theorem using combinatorial formulas for the steady state probabilities. And as I mentioned before, if all the y sub i's are 0, then there's a combinatorial formula for psi sub w in terms of multi-line Qs. This was the result of Arita and Malik. So in this case, and when additionally k is equal to 1, we can use this combinatorial formula to prove this theorem, essentially by mapping multi-line Qs to semi-standard tableau. But for the general situation, for y sub I not 0 and k bigger than 1, we need another technique. And here we're going to use a theorem of Cantini, which basically adds some auxiliary variables into the picture and gives some recursions. So I'll just show his result. So his result upgrades the unnormalized steady state probabilities to quantities with these additional variables z1 through zn, and then gives a recurrence for these quantities. So there's a sort of base case, the quantity associated to the identity permutation is this product here, and then the sort of upgraded steady state probability associated to a permutation SL times W can be obtained from the probability associated to W by applying some kind of isobaric divided difference operator. So that's defined here and is using these extra parameters, the z sub i's. So he has these sort of upgraded steady state probabilities, which have the property that the leading coefficient with respect to z equals the steady state probability psi sub w. And so one can play with this to try to get a handle on what's going on. It's yeah, that's all I want to say about the proof, is that this is a big tool. So now I'll just mention with I'll just end by mentioning a conjecture. So if W is not evil avoiding, then we can write psi sub W as the monomial x to the eta of W times a positive sum of Schubert polynomials. And an open question is there some geometric significance or interpretation to the psi sub w's? You know, since Schubert polynomials represent cohomology classes, and at least based on the data for small n, steady state probabilities seem to be to have this form in terms of sums of positive Schuberts, can we interpret these steady state probabilities geometrically? So that's all I wanted to say. Thank you very much.
Thank you. So are there any questions for Lauren?
Can I ask a quick question?
I did, go ahead.
So in your original model, you had this kind of asymmetry where you allowed to switch the states in one order, but not the other.
Uh-huh.
And what happens if you make that symmetric? Do you still have an interpretation in terms of nice polynomials?
Oh, so let's see. So do you mean, for example, if we were to do this?
Yeah, and then switch it in some other way.
Yeah. Yeah, all of the generalizations I've looked at looked bad. I mean, just experimentally looked bad. Yeah, so I'm not aware of being able to push any of this towards that version, but it would be really nice to make it asymmetric as opposed to totally asymmetric.
Mm-hmm.
Do you have any idea if you replace Schubert's with Grothendieck polynomials, what kind of model you might get?
Yeah, that's a good question. I don't know. And these isobaric divided difference operator, I mean, yeah, we were trying to figure out if the things that we were getting here were related to Grothendieck polynomials. We didn't see any connection to Grothendieck polynomials. And I don't know if there's a way to tweak the model to get Grothendieck polynomials, but it would be really cool to do that. Yeah.
Thank you.
I guess I had one more question, which is if you can find a geometric interpretation of the steady state probabilities, is there any sense in which you could find a geometric interpretation of the whole Markov chain? I mean, the whole process.
Right, right. Yeah, I don't know. You know, I've worked on a different model, a different version of the ASAP, where you have open boundaries. So you have particles hopping right and left, and you have particles hopping in at the left and out at the right. And interestingly, steady state probabilities in this model have to do, well, okay, we can prove that steady state probabilities in this model can be expressed as generating functions for the number of totally non-negative Grassmann cells inside a Schubert variety. Anyway, that you can express steady state probabilities in this model using the combinatoric, the same combinatorial objects that come up in the totally non-negative part of the Grassmannian. And furthermore, one can take this Markov chain. So this is a version of the ASAP where we're only going to have particles and holes, so that every state actually can get identified with a Young diagram. Let's identify this state here with a Young diagram like this. Okay, so a Young diagram to me represents a Schubert variety in the Grassmannian. The combinatorics of the non-negative Grassmannian, well, this has a cell decomposition, and there are tableaux representing cells, which basically are certain fillings of Young diagrams. And one can take this Markov chain, which is a Markov chain on 2 to the n states, and you can sort of lift that to a Markov chain, which is a Markov chain on the tableau representing cells of this cell decomposition. And so you can sort of interpret this ASAP as a Markov chain which is hopping around on cells of the totally non-negative Grassmannian. But I don't really have a good understanding for whether this is a sort of crazy coincidence or whether there's something deeper going on. Yeah, anyway, it would be very cool to sort of interpret the whole Markov chain geometrically. Yeah, in either context, really.
Wait, sorry, Lauren, I spaced out for a second. How did you get to those with the cells of the totally positive?
Right. So this is a cell complex. It has cells which can be labeled by so cells are in bijection with certain tableau called lead diagrams. Their fillings, I don't know, they look something like this. Anyway, one can show that steady state probabilities of this ASAP with open boundaries, steady state probabilities can be written in terms of basically it's generating functions for these combinatorial objects.
And there are 2 to the n of those. Is that right?
No, there's many more of these, but there are 2 to the n states of this ASAP. There's 2 to the n states here because every site can be either occupied by a particle or a hole.
Right, but how did you get 2 to the n from the geometric side?
Oh, only that one can identify Young diagrams with sequences like this. Yeah, so
are those 2-row Young diagrams?
No, arbitrary Young diagrams. Basically the flavor of the result here says that if I'm interested in computing the steady state probability of this state here, I draw this Young diagram, the Young diagram associated to this state, and then I look at all fillings of this Young diagram, which are Lie diagrams. So all of those represent cells of the positive Grassmannian, which lie in a particular Schubert variety. And I have a formula like that.
Great, thank you. Great, thanks.
Yeah, so anyway, so this is a sort of a geometric interpretation that we don't really fully understand.
Thanks very much, Lauren. We might wrap it up there. Can I just remind the audience that the next talk in this series is by Donghyun Kim from Uppsala University, and it's next Thursday, 3:30 p.m. Sydney time. So please join me in thanking Lauren once again for a great talk this morning.
Thanks to all of you.